Thank you all so much for joining us today. The webinar is going to be beginning shortly. In the meantime, I'd love to tell you about some upcoming webinars that we have going on. On April 22nd, we've partnered with the Central Appalachian Regional ERC to offer lean ergonomics. It's an efficiency issue as a part of our NIOSH ERC ergonomics webinar series. We'll also be hosting a webinar on May 6th with Gustavo Plasencia from UC Riverside, who will be presenting a free webinar on From Toxic to Safe, Changing Safety Culture. Our next NIOSH ERC Industrial Hygiene webinar is going to be on May 12th with Dr. Clint Pinion from the Central Appalachian ERC, who will be presenting indoor air quality and net zero energy schools. You can learn more about these webinars online at coeh@berkeley.edu/about-CE. We'll be getting started in just another moment. Thank you all so much for joining us today. On behalf of NIOSH-supported education and research centers throughout the country, we are pleased to present the 2020 Industrial Hygiene webinar series, offering free webinars the second Tuesday of each month. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. We appreciate you being here with us today. Today's webinar, Creative Use of Direct Reading Instruments, is brought to you by the Heartland Center for Occupational Health and Safety and Dr. Tom Peters. A few housekeeping items first. You will be muted during this presentation. If you would like to ask a question, please enter it into the online chat or Q&A. We will save time at the end of the presentation to address all questions. Learners who participate in the full live webinar today will be eligible to receive a certificate of completion. You will receive a follow-up email tomorrow, April 8th, with a link to the online evaluation. Once you complete the online evaluation, you'll be able to access your certificate. This presentation is being recorded and will be made available on the COEH Northern California's YouTube page and on our website. At this time, we're pleased to welcome our presenter. Tom Peters, PhD, CIH, is a professor in occupational and environmental health and biomedical engineering at the University of Iowa. He specializes in developing novel sampling methods that can be applied to understand and control aerosols in the workplace and the environment. In research projects, he's developed a nanoparticle respiratory deposition sampler that collects nanoparticles with efficiency similar to that in the respiratory tract, and a personal diffusion battery to assess exposures to sub-micrometer aerosols. He has also used hazard mapping with direct reading instruments, networks of passive samplers to assess interurban spatial variability of particulate matter, and more recently, through NIOSH funding, low-cost sensors to assess noise, particles, ozone, and carbon monoxide in large manufacturing. Thank you so much for joining us today, Dr. Peters.
Okay, well, thank you very much. As we said before, this talk is creative use of direct reading instruments, or I also call this sensors. So I call sensors modern art for the industrial hygienist. And so I've got a picture of a Jackson Pollock painting here, which is owned by the University of Iowa, and I'll talk about that at the end. Okay, first I'd like to acknowledge some people and sources of funding. Funding sources are NIOSH, Air Force, EPA, NIEHS, and University of Iowa Research Foundation. And then the Iowa's Industrial Hygiene Group. We have many very good students in our department, and they have done a lot of work on the things that I'll talk about. So there's also a large community of researchers working worldwide to protect workers and acknowledge them, especially in this time of COVID. And key collaborators are Geb Thomas, Nate Fethke, Renee Anthony at Iowa, Bill Hyperink and Doug Evans at NIOSH, and Kirsten Kohler at Johns Hopkins. So for an outline, I'll talk about where I have come from, what's the basis of my research and teaching, what have I been up to, research highlights, and where am I going? Current research and future research. So my background, I am an environmental engineer, and I studied aerosol generators for EPA's human exposure chamber back in the day. And so there's actually chambers in Chapel Hill where people are exposed to contaminants. And so I was helping to produce particles for that system. I was an aerosol scientist. I worked in an EPA methods development branch. I worked on developed methods for particulate matter, so ambient air work. And then I went to University of North Carolina. In 2004, I got my PhD in industrial hygiene and aerosol science, and I studied deposition in ventilation ducts. And I've been at Iowa since 2004. So I want to take us way back, and I want to say that science, industrial hygiene is the science and art devoted to anticipation, recognition, evaluation, and control. And look at that first sentence and say, it's the science and the art. And so this art part is often under-addressed, in my opinion. But if we look back and we look at some artwork from my favorite book called De Re Metallica, it was a book written in 1556 by Agricola and translated by the Hoovers, Herbert Hoover and Lou Henry Hoover in 1950. Pliny the Elder talked about the air becomes noxious with depth, which can be remedied by constantly shaking linen cloths, thus setting the air in motion. Now, the cycle of life of an industrial hygienist, there's generation of contaminants, exposure, evaluation, compared to some occupational exposure limit and control. We got epi and tox in the middle. And so let's talk about that for a second. The standard compliance industrial hygiene monitoring, anticipate known hazards, chemicals, dust and gases, physical hazards, noise and radiation, use documented sample and analysis method, collect samples, analyze in a laboratory to obtain time-weighted average exposures, and then compare these values to established occupational exposure limits. The good in this system is that there's many well-known hazards with documented assessment methods and health-based occupational exposure limits. The bad is that there's poor implementation is common. It's difficult to convince people to listen. IH is often understaffed, and it's not good for emerging hazards with no occupational limits. Occupational exposure limits, such as nanoparticles and engineered nanomaterials. And finally, there's the ugly. The regulatory framework encourages small sample sizes. If you take more samples, there's a greater chance of showing non-compliance. So if we look at this plot, we have the probability of non-compliance versus the probability that exposure exceeds the occupational exposure limit. If I have the real probability is 40% that the exposure exceeds the occupational exposure limit, and if I take one sample, then I have a probability of non-compliance is 40%. If I take two samples, it goes up to 60%, 80% for three samples, and so on and so forth. So there's this greater chance of showing non-compliance when I take more samples. And then the expense of sampling, time and money, is also an encourager of small sample size. So as a result, there's little effort expended to explore exposure variability, and the system is driven by the legal system, making change extremely slow. So the solution is we need more measurements in more places to see the forest through the trees, to explore this variability in the exposures. And we need ways to measure exposures to emerging hazards like nanomaterials, for instance. So what have I been up to? We'll talk about some research highlights. Well, I've been trying to make the ultimate sensor package, which is shown here in Spock's hands. And so Spock has been transported down to the Wild West of the United States, or that's what it appears to be. And he has his tricorder, and he's able to measure the biological impact of multiple hazards on human systems. And it's like this wonderful tool that we really could use. I've done a lot of work with aerosols, and so for aerosols, I think the ideal thing would be to measure personal particle number concentration, surface area, and mass concentration by size, by composition, by morphology, something that weighs less than, let's say, 100 grams and can be mounted on a worker's lapel, and then it initially costs less than $1,000 and at minimally recurring costs. All right, so we don't have this yet, but if you have seen one, let me know. What we do have is use of commercial sensor packages. So there's direct reading instruments. They provide a readout of concentration, available for noise, gases, vapors, and particles, often non-compliant, but provide rapid data. The advantages of these sensors is that we can understand the variability of contaminants in the environment. Where are the major sources of contaminants? What are the determinants of exposure? Evaluate exposures and effectiveness of controls rapidly. They can be used to detect concentrations that pose an immediate danger to life and health, such as carbon monoxide, oxygen deficient atmospheres, explosive environments. And then they provide an effective way to communicate risk as well. There's considerations when using sensors. One is data validation. There's an enormous amount of data, and it requires some kind of portable verification devices. A range of sensitivity, range of detection and sensitivity, concentration, size of particles is important, and specificity. You can detect certain specific chemicals, but not others. And then there's also problems of detecting the wrong chemical when you think you're detecting the one you want. There's a lag time between the environment and reading that sometimes may make a difference, and it may not. Oftentimes these readings are very rapid. And then there's physical limitations of the instrument, the weight and battery life. And is it affected by the environment, such as temperature, relative humidity, wind? All these things can cause sensors to read the wrong values. What we use them for is hazard mapping, one of the things we've done. And hazard mapping provides a set of eyeballs unavailable traditionally. It provides a general sense of contaminant concentrations, sources, and fate, and it shifts the focus from single measurement to big picture. So this example here is John Snow's work, where he was looking at cholera transmission from the Broad Street pump throughout the community. And so he was trying to map these exposures in order to get a better handle on where the source was. We do things in a similar way, where we're taking measurements throughout a workplace, so measurement location, and then we in magenta, and we go throughout the plant, record position, record data for a certain time, walk through the entire plant, create a spreadsheet, X, Y, and data, and then we can create a map. These maps gives us here's some example maps, interpreting maps. So we have here this process in red is much stronger, higher concentrations than in white, and green is just a little bit of concentration. So here, this would be process 2 is a hot spot. So then we can examine controls and work practices where in that one location. Now, let's say instead there's hotspots that are outside of the air cleaners. So then we can examine the air cleaners. And then if there's no clear hotspots, we can consider general ventilation as a solution. Other thing we can do is monitor over time. So we can look, and there's percent floor space versus concentration in arbitrary units. So this is an actual example of aerosol concentration in milligrams per meter cubed from a large industrial factory. So here we have post control number 1. So we have, first we have the initial evaluation in red. The initial evaluation in red shows that there's 50% of the values are above 0.5 units. And then if I go up here about 90%, I have 10% are somewhere between 1 and 2 milligrams per meter cubed. After controls, the controls worked well. They reduced concentration a lot. We have 50% value of around 0.25. And then after a month later, we tested the system again, and we were able to see that the controls were still working. So there's a way now in order to rapidly test before and after implementation of a control, and then after time to see if the control is actually working. This is early when I got to Iowa. We put together this sampling cart, and we went to a engine manufacturing facility that was making 800 diesel engines a day. And so we went through, we have direct reading instruments for different types of particles. And so we have, one is a number concentration counter, and one was a surface area concentration counter, and another one was a mass concentration counter. And so we have number concentration in this facility in the winter and the spring. we see one area that's quite clean and another area that's kind of medium contamination. This is around 400,000 particles per centimeter cubed. And then one area is just getting hammered by particle load. And these are on the order of 1 million particles per centimeter cubed. But in the winter, you've got this going on. In the spring, there's number concentration is very low. If I look at winter by another metric, so number concentration versus mass concentration, I can see that I have a totally different picture where this is still clean, this area is clean, but this big red blob by number, the little tiny particles don't weigh anything. And so I can't see them. Where I can see particles in this area where there's oil machining going on with oil and oil mist as a contaminant. We were able to figure out that the natural burning natural gas for heat was the cause of this area, this red blip. But the hazard mapping allowed us to be able to see these different areas of the facility. We're also able to measure these different metrics again and get a different picture of where you might put your resources. So here, this is a foundry, and there's a core room, melt, pouring, clean room, and then shakeout. So by number concentration, I would look at melt and the core room. By surface area concentration, I would put my efforts in the core room and over in this area. Then by mass, I would look at the pour area and the cleaning room. So which metric is most important is unclear. And so we've got some different notions of what should be toxicologically most important. But the mass concentration is what we do regulations on. We've used mapping with different sensors to help understand the issue. And so here, this is in a swine barn. And so we have a photometer to give us mass concentration. We also have temperature and carbon dioxide. And so this was in the winter. The profiles were very similar, and ventilation issues were likely very important in this situation. Okay, so that's hazard mapping. Now we can also take our sensors, and we can put them near processes, and we can do task-based monitoring. So we've got, this is a nanomaterial production facility. So we had a condensation particle counter, number concentration by time. And we have a photometer, mass concentration by time. And we're able to see that the number concentrations do not correlate with the filling of a hopper or the change out of bags and filling a hopper. So, but we do look at the photometer output, and we can see that the mass concentration is very directly related to the process. So our mass, not numbers related to tasks, thus not a nanoparticle issue. All right, so now we've I have a video of another process that I would like to show you. And this is the start of a partnership with ergonomics professor at Iowa, Nate Fethke. Let me show you this. This is tests conducted at an ironworkers union training center. So this is the process of stud welding, and studs are put into this decking material in order to hold concrete onto steel beams. And that was a mistake on that last one. And so there was a short, but there is awful posture that can lead to back problems in this type of work. And fumes are coming out every time a stud is put into the metal. And so that's generally not recommended either. So we tried to think of engineering a better way to put these studs in. And so what we did was we had a tool balancer. And so we took the tool balancer, we've got the person holding bicycle handlebars and running the drill, running the stud gun remotely, so that he's able to keep his body upright, and he's also able to keep his breathing zone out of the fume. So it looked good qualitatively, and we had this person was quantitatively being measured at the same time. And so we've got a ergometric is trunk inclination. So here's with the new system, there's 0 inclination. And then with the conventional system, we've got minus 100%, 100 degrees inclination. If you look at the fume exposures, this is 1 times 10 to the 6, that's 1,000,000 particles per cc. And so this is very, you don't hit that ever when you have the new system. There is still some spikes occasionally. And, but with the conventional system, we're over 2 million particles per cc each time. And we were really excited to be able to be on the cover of the Annals of Occupational Hygiene for that one. Okay, so where am I going? We've got a collaboration with Geb Thomas Engineering at Iowa and Kirsten Kohler, and we are looking at sensor air quality network in manufacturing. So we're kind of shifting from commercial instruments, use of commercial instruments, and shifting into purchasing them ourselves and making our own monitors. So one of our recent projects is to estimate personal exposures. And so we're moving from doing roving monitoring where we have one monitor and we're moving around the facility to get a map, and we're going to have multiple monitors all over the facility, and we're going to get a time series of hazard maps, and then take worker location tracking data and integrate those two things, and then generate personal exposure. And so I'll show you what we've been up to here. So the monitor, we've got a PM 2.5 particle sensor, microcomputer to do all the data acquisition, temperature, relative humidity, oxidative gases, ozone and NO2. That's proven to be quite a problem sensor for us. Carbon monoxide, and then a noise sensor. One of the things that we do in our tests is evaluate sensors for occupational conditions. So there's a lot of people doing sensor work in ambient air, but there's not as many doing work in occupational settings. So we test our sensors in occupational settings. One of the things we found with this particular sensor, the SHARP sensor, there is the sensor that was active had a lot of noticeable sensor drift after this 0, 1, 2, 3, 4, that's months. And so after about half a month, we got substantial drift and the sensor never came back again. Our passive sampler was able to go for much longer duration. And so what we get in this is we get an hourly average over one day. And so this is a facility where there's welding of large automotive parts. And these parts are, there's cutting of metal, there's machining of metal, and then machining and assembly, and then more machining. So here's the concentrations. In the very early morning, we've got very low concentrations. As we come into the day, we have much higher concentrations. Lunchtime, things go down, and then quitting time, and so then we've got our low concentrations again. So this is particulate matter, and these are hourly averages. So if we look at snapshots of that video, we've got 4 to 5 a.m., we've got concentrations are low. 6 to 7, people get to work, they start working, ramping up concentrations. And then finally quitting time, we've got concentrations go down. So we get similar patterns throughout the summer. General ventilation is insufficient to keep up with contaminant generation, and its lowest concentrations are lowest in areas with full enclosures, not particularly surprising. What we did then is to collect personal measurements for mobile employees. And so we were not able to actually track employees. So what we did was we took our own study staff and we wore reference instruments around the facility. So we took and measured particulate matter, CO, ozone, and noise. And we measured those things at high frequency around once per second to 10 seconds logging interval. And then we went along and followed employees in order to get the measurements for the mobile employees, the personal measurements. So we took and then integrated that location with our hazard maps, and we obtained a time-weighted average exposure, or an exposure for each time, and then we calculated a time-weighted average personal exposure. If we look at the network-derived estimate versus the reference instrument estimate, we have particulate matter on the y-axis versus time. And so we've got are in blue is the reference instrument. In orange is the network derived instrument. And we actually get an up and down. We're able to derive an estimate which is reasonable compared to reference values. Where we want to go is to promote health. And so far, we've been making a lot of measurements. We've had some successes in terms of, making people aware of their environment and making them aware of where they may want to put resources. But what we really want to do is to be able to promote health in some way, in a more active way. So we want to measure personal exposures, attribute exposures to specific locations, and then link health effects to exposures. Now, that's not easy, and it's been something that's I've been trying to move towards for quite some time. What we have done is we have tried to put together a system that we have now is an autonomous hazard awareness training system. And this system is in a, well, let me describe the system. So we have a monitor on a farmer, and the farmer wears this monitor, and you get some kind of signal, which is a noise in decibels versus time. At the end of the high level, we ask, what activity were you involved in over the last X minutes, and did you wear hearing protection? We've modified the system somewhat to be more automated, but there's a smartphone app, and that actually now is a laptop computer in order to get things to work. We have internal processing, observation, collect the data, learning, determine hazardous activities, predicting, using learning to tailor instruction. And then our external interface, a summary of data by hour, by day, by month. And we have map data and suggestions for PPE use and placement. So in order to make that happen, we developed a low-cost personal noise monitor. And this low-cost personal noise monitor is $25 in components. And if you look at the noise measured by the monitor versus the reference instrument, you get good agreement from 70 to around 95 dBA. And so that's right where you really need it to be good. So that allows us to have many noise monitors in an environment. And this monitor will take the sound that's measured in the environment. We got intensity versus time. Goes through a FFT, Fourier transformation, and that changes, and we look at the power spectrum, and then we're able to get the dBA measurement. So we've taken the sound level meter now, and this is a personal version. So there's monitors that are used in stationary installations, and then we have a personal monitor, and we're doing this in tandem. And so the Ulowa personal monitor, there's a particulate matter sensor on this instrument, accelerometer to measure, acceleration, temperature and humidity, again, the sound level meter, and an aggregator and real-time stamped data storage. So these things, these are all, the components are getting smaller. And this here was a breadboard prototype that we used. That's not so important. But what we've done with the personal monitor is we've got 1 hertz sampling for PM and relative humidity and temperature. Those things we're able to, 1 hertz is just fine. That's like a lot of data. Things don't change that fast. Acceleration, 25 hertz sampling. And then sound, we're doing 44 kilohertz sampling. And that's in order to get the data so we can do the Fourier fast transform on the data. We store all this data on a micro SD card. We've been trying now to automatically detect tasks. So what is the person doing? And instead of asking people what they're doing, to actually automatically detect it. Kind of like on your phone knows that I have an app on my phone that knows if I'm walking, it knows if I'm rollerblading, it knows all these different kind of things from the accelerometer data. So we take and look at the initial work. This is a feasibility study, 8 subjects, 6 tasks, and 3 trials per task. We're looking at driving 30 fasteners versus with an electric drill, drive 30 fasteners with an impact driver. So that's a comparison that has similar acceleration but different sound. Then there's 2A and 2B, that's driving nails. One is with a hammer and one is with a pneumatic nail gun. That's different accelerations and different sounds. And then I've got the last one is move a vacuum nozzle slowly, move a vacuum nozzle quickly. And so we have a different acceleration but similar sound. So we're trying to see if we can use acceleration and sound to figure out what the tasks are. Yeah, let's keep going. So this is our data that we can obtain. And this is acceleration in the time domain on the left, acceleration versus time, and the audio in the frequency domain is on the right. So the amplitude versus frequency of noise. So here's in the time domain, if we look at, this is the standard drill versus the impact drill. The blue is up here around 1, it's up here also 1. So this is, all of these lines are very similar. Whereas in the audio domain, the standard drill is much different than the impact drill. The impact drill has a lot more noise, more frequencies in the higher, more power in the higher frequencies. If we look at a hammer versus a pneumatic nail gun, clear differences in the profile and the audio. And we've also got clear differences in the acceleration in the time domain. So here, red is substantially shifted compared to the green signal. And then the slow vacuum versus the fast vacuum, we've got different accelerations, similar sounds. The way we did we moved back and forth to left, to the right, to the left, to the right. And so we wound up having a cyclical pattern, looks like a sine wave. And that produced the audio is fairly constant because it's the shop vac and that's not moving. So if we look at all this together and can we classify these tasks, and we can look at a standard electric drill driver, impact driver, if we use the accelerometer data only for the electric drill, we get 90% model accuracy. That's pretty darn good. If we use audio only, we get 73%, but if we put them both together, we get 91%. That's good. It's not that big of a difference between accelerometer only. But here we've got like impact driver, 62% for the accelerometer only versus 77% for the audio only. And then we have 92% detection for them both together when our model has both signals. So you can look and we wind up getting pretty good detection ability when we combine the accelerometer with the audio. So what we're thinking is we can ruggedize this. We've got a May collection, which probably will not happen, and then field data collection in the summer, but we are thinking that may get pushed off as well. But with this system, now we're able to have a measurement of the hazard, and then we're also able to try and understand what people are doing when the hazard occurs. And so that we can automatically do a determinants of exposure exercise. And that's our goal. So to summarize, we've creatively used sensors and it supplements traditional compliance monitoring. It provides data on environmental variability with relatively low cost, critical and absence of no working exposure limits or inadequate exposure measurement devices. And then I say it represents this modern art for the industrial hygienist. Now, if you'll bear with me, we'll go back to this painting, and this is a Pollock painting, which I showed you originally. And this painting reminds me of hazard mapping, #1. And the painting also has a dubious history. It was originally sold to the University of Iowa by Peggy Guggenheim, who commissioned it by Pollock. And it was in the basement of the art building, which flooded in the flood we had here. But it was removed clandestinely, and so it's been on a world tour since then. But one of the interesting things about it is that in this painting, if you remove layers, you never know what you might see. And so there's you can see a Jackson Pollock if you remove different layers of paint. And it's in an arts journal, which I think is quite interesting. And so with creative use of direct reading instruments, I think that you never know what you're gonna see. That's my talk for today.
Thank you so much for that presentation. At this time, we do have time for some questions and answers, so you're welcome to enter any questions you might have into the online chat or Q&A box. And we do have a couple of questions that have already come in. The first, in the machining welding facility, were there any readings done in the office and or break room to see occupational bystander exposure?
Machining, welding, so this work here, I think is what's being referred to. And we made measurements in a position that was way over to the right in a paint area. And so but we don't have it in the offices.
Thank you. Another question, how was the mapping done using the data from the dust sensors?
So it's pretty straightforward, just taking the X, Y, and Z values and we've used a couple of different programs, like a Surfer is a program I particularly like, and it's made by Golden Software, and does a nice job with making this contour map. There's a lot of this work here is done in MATLAB. It's a little bit complicated and doesn't come out looking that great in Excel, in my opinion.
Thank you. A follow-up question on that. Someone also asked if you could speak a little more about how you created the model in your analysis, and have you used ANOVA?
In which analysis?
Oh, that is a great question. They didn't elaborate. I just said creating the model and analysis. So that person who asked the question, if you want to specify which analysis, you're welcome to do so. And in the meantime, we can go to, the results table where the variations in type of tools were used.
So this model is a machine learning model. And the machine learning model is, I don't understand. Oh, an ANOVA method? No, we didn't use an ANOVA method.
Great, thank you. We have a comment that says, thank you for a very interesting presentation. They also appreciate the Pollock dissection. Another question, how do you address the calibration of these sensors, if any?
Yeah, so calibration is super important. And when we've had the sensors in for long installations, we go out every month and we check with comparison to reference instruments. And so we look at the difference, and if the difference is a certain magnitude out, we take that sensor offline and put a new sensor in.
Thank you. Do you have any experience trying to integrate noise dosimetry data with GPS positioning?
So I have not been working outside very much, and the GPS, is primarily an outdoor signal. So we've had to rely on other methods than GPS.
Great, thank you. Someone wanted to follow up on the art. Do you have any opinion about whether art can be a means of public health and occupational communication?
Oh, I love it. One of the, is it Monet? I think it's Monet painted the London Bridge in different conditions. And he had wonderful, you could see the light scattering, and definitely it's a way to communicate. Art can be a way to communicate.
Thank you. We also have another question regarding your sample collection period times. And for this person, would you like to specify for, I guess, which Which samples?
I can guess,
Okay, great.
and I'm guessing this. So we, when we were in this facility and we would have the collection time for this person would be a shift. So whatever shift the person they were following was working is how long we would sample.
Great, thank you. We do have a few more minutes. If anyone else has any questions, you are welcome to enter that into the chat or the Q&A box. And while we're waiting for more questions to come in, I have a question myself. Based on the studies that you've done, is there an area that you're really looking forward to or that you're hoping to study next?
Well, I am particularly interested to in taking this personal monitor and relating particulate matter measurements with the tasks that people are doing. So right now we're kind of in the weeds, I would call it, of trying to do these task measurements and validate task measurements. But I think it's going to be really cool to see the hazards and how they relate to the different tasks.
Thank you. Another question has come in. Can this type of hazard mapping be used with other types of direct reading instruments, such as PIDs?
Absolutely. It's any instrument that gives you some output of concentration. There is one note. Some instruments have a lot longer time lags between when they sample and when they measure. So you got to be a little bit careful about that.
Great, thank you. Another follow-up question, what is the role of exposed workers versus engineers in the process?
The role, what is the role of exposed workers versus engineers? By engineers, do you mean our study staff?
Yes.
And by role, do you mean like a IRB issue or?
They said defining exposures of concern.
Oh, I guess I'm not sure. I still don't really understand the question. I think that we really wanted to be able to measure on subjects in the facility. We had a IRB established to do that, but we wound up getting into issues with the company not wanting the measurements to be done.
Thank you very much. And we have one more question. Did you use any specific dust, something like Arizona dust, for the calibration of the dust sensors?
Yeah, so what we wound up doing was using, we first figured out whether or not the sensors had, what were their limits of being able to detect different particle sizes. And then we ultimately used salt aerosols, and we bought 100 sensors in order to pick 50 of them that worked the same. And so it was a process in order to measure the reading. What we wound up doing for the measurements at the facility was we would take and we corrected to gravimetric measurements. So we had gravimetric measurements side by side with the monitors in the facility. Not every one of them, but we had several of them, and we evaluated the relationship between the light scattering signal and the true mass concentration.
Great. Well, thank you so much for your information today and for answering these questions. Also, thank you to everyone who joined us for today's webinar. As a reminder, the NIOSH Education and Research Center Industrial Webinar Series takes place at the second Tuesday of every month. This new series is in addition to our NIOSH ERC Ergonomics webinar series, which takes place the third Wednesday of each month. Our next industrial hygiene specific webinar will be on May 12th with Dr. Clint Pinion from the Central Appalachian ERC, who will be presenting on indoor air quality and net zero energy schools. You can learn more on our website at coeh.berkeley.edu/about-CE. Thank you again all so much for your wonderful questions and participation in today's webinar, and a special thank you to Dr. Peters. I hope you all have a wonderful rest of the day.